In the video on map, I showed you how this is a function that takes a number in one range and turns it into the corresponding number in another range. That's kind of an abstract thing to do, so we talked about how you might use that to establish a correspondence between points on a data tablet and points on the screen. We said you could take the whole data tablet and map it to the entire screen, meaning every point on the data tablet goes to a point on the screen, and there's a correspondence so that if you tap, say, in the upper right of the tablet, you see a mark in the upper right of the screen. But you could also just choose pieces of this. So you could say, you know what, I just want the dark yellow rectangle to map to the entirety of the display, or even I want the dark yellow rectangle to map to the dark red part of the display. All we're doing is taking a point in the dark yellow rectangle and finding its corresponding point in the dark red one. And we use map to do that. In fact, we would use two calls to map. One call to map the X value from its location on the tablet to its location on the screen, and a second call to map the Y value. I also said you could use map to do color replacement, where we would map a given pixel, say this green pixel on his green shirt, to a corresponding color, say purple, in the second picture. To do this, I would call map 3 times to transform the red, green, and blue components of the input pixel into the red, green, and blue components of the output pixel. Abstractly, we can look at it this way. Now I'm trying to make it very abstract. At the top, we can see map takes an input value v and an input range, which I'm marking in red, which is defined by a start and end. These are just numbers. And an output range, which also has a start and an end. We find the location of the value in the input range, the red one, which here I've marked with a solid red dot, and we simply find its corresponding location in the output range. Here I've marked it with a solid blue dot. The value of the blue dot is the value of map. That's all map does. This is admittedly kind of an abstract thing, so I'd like to show you a couple of examples of using map in sketches. This sketch has 3 parts. On the left, we have a sun, and we'll see that the sun rises in the sky and then sets. On the right, we have a clock, and under the clock, I have a slider, and I can adjust the time by moving the slider. At the top, we have the map statement. What I'm doing here is I'm using map to turn the time into the angle of the sun. Let me just move around the time slider and you'll see what I mean. As the day goes on and the clock goes forward throughout the day, the sun rises. At exactly noon, the sun is directly overhead. And then as the afternoon goes on, and I'm keeping 24-hour time here, so this 2 o'clock is 1400 hours, 3 o'clock is 1500 hours. As the day goes on, the sun sets until we get all the way to 1800 hours or 6 o'clock p.m. Whoops, I get right there, and the sun has set. If I go all the way back to 6 a.m., we can see that the sun is just rising. Let's get to 6 o'clock a.m. There it is, and the sun is just on the horizon. So I'll tell you what, let's work our way up to about 9 a.m. How do I know the angle of the sun? Look at the line at the very top. I'm mapping 9.0. That's the current time. And I'm turning the hour and minutes into a single number. So if it was, say, 9:30, that would be 9.5. If it was 9:15, it would be 9.25. So that time is my first input to map. That's the number that I'm mapping. The input range is 6 to 18. That represents sunrise and sunset. The time 6 means 6 a.m. The time 18 means 1800 hours or 6 p.m. The output range is 180 to 360. That's the angle that the sun makes with the horizon. Right now it's 9 a.m., so we're a quarter of the way through the sun's cycle on this perfect day. And the output, 225 degrees, is a quarter of the way from 180 degrees to 360 degrees. If we work our way up to exactly noon, we're now halfway between 6 a.m. and 6 p.m., and so the output is exactly halfway between 180 degrees and 360 degrees. Finally, if we get our way out to 3 p.m., which is 1500 hours, we are now 3/4 of the way from 6 a.m. to 6 p.m., and the output is 3/4 of the way from 180 degrees to 360 degrees. So map lets me take the current time expressed as a number in the range 6 to 18, and it turns that into an angle from 180 to 360. And then I just draw the sun at that angle. So as I move on towards the evening, the time goes up and the angle of the sun goes closer and closer to 360 degrees until at 6 p.m. it hits 360. And if I back off time, as we go back earlier and earlier in the day, of course, the time becomes earlier and earlier, and the output of map becomes a number that's closer and closer to 180, which is the start of the output range. Until right here at sunrise, 6 o'clock exactly, we are at 180 degrees. This little sketch lets me convert degrees from Fahrenheit to Celsius and back again. I drew the gradients as blue to red because I wanted to suggest the idea that these ranges cover the range of water from ice on the left to boiling on the right. I can grab the big circles at the top and the bottom and drag them around with my mouse. So let's grab the Fahrenheit slider, and I'm going to drag it left down to 32 degrees Fahrenheit, which is the freezing point for water. And I'll try to get right up to 32 degrees, and there we are. And you can see that's 0 degrees Celsius. As I move the Fahrenheit slider to the right, the centigrade slider moves to the right as well. And I'm using map to find the corresponding value in the Celsius range given the Fahrenheit range. So water boils at 212 degrees Fahrenheit, and there we are at 100 degrees Celsius. This is nothing more than a one-line call to map. I take my input value, number of degrees Fahrenheit, the input range, 32 to 212, and the output range, 0 to 100. And out comes a temperature Celsius for any input temperature Fahrenheit. Let's look at another example. In this sketch, I'm going to do exactly what we saw in an earlier slide where I mapped a section of a data tablet to a section of a screen. Let's suppose that this graphics window is my data tablet, and the brown circle represents the location of my pen. This dark rectangle represents my output screen, and the blue circle inside of it represents the cursor that is tracking my pen, such that if I were to start drawing, that little blue dot shows me where the marks would begin to appear. As I move my input point around on the data tablet, notice that the little blue dot, which is our output point, is tracking me. When I'm in the upper right corner of the data tablet, the output point is in the upper right corner of the screen. When I'm in the upper left of the tablet, it's in the upper left of the screen, and it's true for all the corners. The location of the brown circle, of course, is nothing more than mouse X and mouse Y. So I have a little mouse handler routine, in this case, mouse dragged. So every time mouse dragged gets called, I make 2 calls to map. In the first call, I take the value of mouse X. The input range is 0 to width, the width of the graphics window, and the output range is the left to right side of the little inset dark gray window. Then I make a second call to map, where I map mouse Y from 0 to height, the vertical extent of the graphics window, to the vertical extents of the dark gray window. The results of those 2 calls to map lets me transform mouse X and mouse Y from values in the graphics window to values in the dark gray window. I save those 2 resulting values. Later, when draw gets called, I simply draw a little blue circle at those coordinates. That's all there is to it. So map is really just a little convenience function. It lets you take a value and transform it from one range to another range. Once you get familiar with this idea, it will be as convenient for you to use as addition and subtraction. And in fact, you'll find yourself using it all the time. It really is a terrific little general purpose tool.